Got
All
it.
right, thank you, David. So we're gonna get started here as people kind of come in and out. I know they like to do that and see if that's interesting for the people. So today we're gonna look at the motion magic. We're the Grand City Gearheads out of St. Cloud, Minnesota. First, like to just thank Medtronic and Delta ModTech and then St. Cloud State in December for hosting these events. It's great that we can still get out and reach so many students and mentors across the world now with this virtual presentation. So a little bit, my name is Applegate again. Been a mentor with the Grand City Gearheads for 6 seasons now, 22 years as a controls technician. And I've beta tested a little bit of the Limelight and now the Glowworm. So it's kind of a continuation from Green Machine's vision process where they didn't slam on the Limelight, but it's definitely an easy solution. So we can talk about that next month. I've been a VS Code beta tester, and this last year kind of been contributing to the WPI libraries. Today in the back of the classroom, I have some moderators in the chat room, so get those questions out. They'll read them out to me and we'll answer those as we go along. So that would be Justin Fisher and Carter Calhoun. They're both alumni of First, and there's their team members. And then Zach Usplund is also along with us here. So let's get right into the motion magic. So how do we control our robots out there? Primary 2 ways. We can do things with open loop. It's no feedback and not measurably repeatable. So if you want to pick and place, and 2 years ago, or not last season, but the 2 seasons prior to that, we had a lot of pick and place applications. So we had elevators and arms. Not so much this year, but there are a few applications where we do want to go into this closed loop. Closed loop, there's 2 primary areas, velocity and position. The set point, we define a set point and the process calculates the error and closes the control loop to get us to where we want to go. Ways we do that is with PID, and then there's also the F also thrown up there sometime, the feed forward. Motion Magic, the Crossroad Electronics platform, that's what we're going to focus on today, and also motion profiling where we can get a little bit more control of the whole curvature of where we're going. These closed loops are measurably repeatable. So if we want to continue to repeat an action, pick from the same place, and pick and place at the same point, this is where we're going to want to do. What a PID loop would look like is if we go to we set our command position, the output is set at max speed, and as we get closer to our target, our speed will start to slope off until we finally make our target. We can control max speed sometimes, but it's really in this acceleration zone. If we're moving a heavy weighted game piece, you're really putting a lot of stress on the mechanics of it. So you want to start looking at maybe a better control system like Motion Magic, where we can define an acceleration, define a top speed, and then define the deceleration as we get there. A lot more smoother control of our mechanisms. And then motion profiling, where through the process of getting to our set point, we can tell how fast to go at that point, maybe cruise along or hold there for some time, move again, and we have ultimate control throughout the whole process. What we'll cover, we're gonna look at the sample code from Crossroad Electronics. And we're gonna check our motor sensor polarities. When we set up a motor and a sensor to our devices, they have to be at what we call in phase. We're gonna look at the feed forward term and how to calculate that. We're gonna set our Motion Magic cruise velocities, accelerations, our P, I, and D variables, and finally we'll take a look at some arbitrary feed forward to remove gravity. Some of the tools we're gonna use here, and we're gonna just hammer through these slides before we get to the live demo. We're gonna look at the Phoenix Tuner, primarily the plot tab, is where a lot of information can be collected for our Motion Magic. We're gonna use the console output to collect some data. We're not gonna use shuffleboard, but it can be used also to collect these same things that the console is gonna tell us. Where to get the code, you want to get that at CTRE's sample code library. It's posted on the GitHub and their links are on their website and is here as well. And finally, we'll take a look at our Motion Magic worksheet that the Gearheads have created to dump in these few variables, and it will output what our feed forward terms are, our PI and D, cruise velocities, as well as do some sanity checks for us. So we're going to look at, when we go into the sample code, we're going to look at where to set the can, because in the sample code, it's not set up for your robot. So there are some tweaks that you're going to have to do to make it match your robot you have in front of you. So we'll set the can address, the joystick address. We'll comment out any followers that may be in your system or may not be in your system. We'll configure the feedback sensor. It is configured by default for the magnetic encoder, but today we're using an analog potentiometer. We'll check that motor phase and sensor phase. We'll zero all the PID values and zero our cruise velocities. We're also going to look at the bottom here of how we might zero our sensors. If we're using an encoder, we will have to do a homing or a reference routine. Todd Cruz kind of touched the base on that a little bit. You heard that term in there when they were doing the walkthrough on that machinery. If your elevator starts in the mid position, if your robot does a reboot in the middle of the match, that is now your new zero. You're going to find a way to zero it out. So you can use over travel sensors to re-zero your feedback. And I'll also look at so feedback not continuous. For our case, we're using an analog potentiometer, so we'll set that true. And then also not included in the sample code is some variables to set for your motors. If you want to protect a motor for stall, there's some great videos out there, and there's a link here, and also in the chat room, my moderator will be posting some links to a handout that you'll want to print out. Adam Hurd from 973, a great video out there on how to size your motors and gearboxes so you don't catch them on fire. And finally, you're going to want to set your motors to brake mode or coast. Really important on your application. As well, if you're going to use the I term, you're going to want to set your integral zone. So we're going to skip the slides because that's the boring stuff in my case. And bring over the sample code. So when you go to CTREs and you go to their website and download their sample code, you're gonna open up what they call Motion Magic. And there's a ton of different files in there. So depending on the application you're trying to focus on, you can download and look at their sample code. But right at the top, you can see that they had set their Talon SRX to port or CAN ID number 1. In our case today, we're gonna use 13. And also the joystick 0. They also include a couple followers. And again, on our elevator that we have here today is that we have a follower motor on port 15, as well as, and we don't have any other motors, so we start to comment them out as needed. Scrolling on further down, you see when we commented those out, there's some errors, so we'll continue on here. I'm not gonna do this perfect here all day long. We're gonna open up the ready-made file. And we'll change our encoder to an analog encoder. The rest of this stuff here is where we're going to check to see if our sensor is in phase and flip our sensor. If it is backwards, we can turn our motor. If we give it a positive command, we would like our elevator to do a logical positive direction. As well as down here, these constants, I tend to, when I'm running the sample code, zero them out right here, but you could also go to the constants folder and zero them out there. Our cruise velocities, we want to zero all of these out so we can start with fresh numbers that's relevant to the robot that we have in front of us today. Those are the changes that we want to make to the sample code. And then kind of browsing through the teleop periodic method here in this robot. You can see up here, they're getting a couple joysticks. They're setting some dead bands. They're collecting a bunch of data for the console for us to read, as well as when a button 1 is pushed, we're going to go to a target position. Now, I recommend if you're going to run the Motion Magic test code for the first time, you do it on a mechanism like a drivetrain that has infinite monorotation, doesn't have hard stops. Because you can imagine if you overdrove a mechanism to its hard stops, things could begin to break and melt down. So here's what they're doing is they're taking the joystick value times the magnetic encoder's revolution of 4096 times 10. So -1 to +1 would rotate that output -10 rotations to +10 rotations. And they're setting their talon to control mode and motion magic into whatever that target position is. So as you sweep through the joystick, it would follow your joystick's analog position. And then it's outputting some more information for us to collect. And my monitor just went dead there. You still collecting over there? Yeah, but my technical deal, there it is. But now I'm dragging it off, aren't I? Yeah, the projector just went off on me. If I unplug this, excuse us for a second here. Are you collecting my main screen now? Oh, I see that over there. No, because I had a cooldown. That was like a 4-minute cooldown. Okay, pull up the video, live video. Yeah, that's where I was going. Are you seeing my, there it is. Okay, we're back. All right. All right. Sorry about that. Thanks for being so patient here. So we are just looking at the when button one's pushed, it follows the joystick. And if no buttons are pushed, you set your talon to % mode and you would just jog the motor like you'd normally would -1 to 1 or -100% to 100%. Down here in the bottom is a way to zero our sensor. So if we do have an encoder, we can re-zero things as well as setting some smoothing. And we can, that's how much jerk we call at the beginning and end of our slopes. All right. So that was the code as it is downloaded out of the box. Here's our code with the changes that we're going to use. So as we can see at the top here, we added these 2 new variables because we're going to be using an elevator today. So we have the min position, the down position, and the max position is 700. And I'll show you where we can get those numbers. Our talons are set. Everything's set as our robot is. Our analog device here. Our sensor position set to true right now. Everything's zeroed out. Nothing else has changed up there. Here's where I was talking about. We're not gonna set our talon to 0 on power up because we have the analog encoder. So anytime we power this robot up, even if it's extended or retracted, we'll have that same position. Absolute. With that analog sensor, we're gonna set the non-continuous so that way it doesn't roll over from 1096 to 0 if we hit that threshold. The motor's max current to protect our system, and also the integral zone set to 3. Up here, we didn't really change much in the joystick collection area. These variables here to output some information we're going to take a look at. We did add a couple lines here. We want to output the position. We want to know so we can go and set our variables at the top here to what's actually going on on the robot. And down here, button 1, we commented out the joystick calculation, and we're just going to set our target position to the min. Button 1 is the A button on our Xbox controller, as well as we put an else if button 4 button Y, that would be to the max position to control the elevator to the 2 set points. And then still the else function. If no buttons are pressed, we can jog it open loop style. Here at the bottom later on, we're going to get into the feed forward terms. So once we made these changes, we set our positions or our addresses for our encoders, we're going to go ahead and thought the robot was on, so I'm shut it off. Wait a second here for the robot to boot up. The key why this is booting up here is to go in here and configure this sample code just as if it was, or just for your robot. The CAN addresses, the joystick controllers, zero all these variables because we're going to calculate those in a minute. All right, let's try that. Should get enough time. As this is downloading, it's really important when you're building these mechanisms to include encoders or feedback devices during the design stage. Even if you don't know how to do this, having those components on your robot ready to go when you do ask for that help, that in the pits, when somebody comes along there, it's like, if you have this encoder, a CSA can sit down and work with one of the students, or even one of the other students from one of the other teams can sit down and help you figure out how to make your robots smarter. Now that that's downloaded, I'll pull up our driver station here and the console window. Clear this. We can go ahead and enable our robot. The first thing we want to do is push up on our joystick. We're going to do our check our motor and sensor phasing. Pushing up on the joystick, we can see that the Talon SRX is flashing green, which is a positive direction, and our elevator is going in a logical positive direction. That's one of the first things that's important for us, just so everything stays logical. Now that we know that positive command does a positive direction on our robot, we're going to open up the Phoenix Tuner tool. And we're going to go to the plot tab. And from the plot tab, we're going to select the Talon that has our feedback device. And we're going to enable the plot. And now we can see as I push up on this joystick, disable the plot here, we can see as the blue line here is our positive output, our position is going in a negative direction. So our motor and our feedback device are what we call out of phase. Well, since our motor is going in a positive direction on a positive command, and the elevator is going up, we know that that part's correct. So we have to flip our sensor. So a few people can write in the chat room there, where would we flip that? As I go over to there. Anybody? I know we're drilling through code here. It can get kind of boring at times. In the constructor, sure. In the constructor here, we have the Talon set sensor phase, and we can see it's set to true right now. We're going to flip this over to false. Hit save. And we're going to re-download this code into our robot. You can see in the picture-in-picture that that robot is halfway up, which means if we would have left this line here uncommented, that this would be now our new 0 position. And since we're using an analog feedback device, we'll know exactly where this robot is, even on a power up. Bringing up the driver station again once this is finished is we're going to go ahead and check this again. Down, down, up is up. Bring up the Phoenix tuner, start our plot. And now we can see as we push up, our analog, our feedback device is also going in a positive direction. So now our motor output and our feedback is in sync with each other. And we can be done with this tool. Here we can run this all the way to the bottom and try to read where our sensor position currently is. But if you remember, we added that to our code here to tell us our current sensor position is at 20. And if we go all the way to the top, we're roughly 730. So to be safe, we're going to go to 700. So we're going to record those values down on our piece of paper, and we'll return to the code here in a little bit. There's another number we can test right now. Now that we know our sensor and motor are in phase, is we're going to collect what is the max speed of this mechanism right now. And this is where it gets scary here. Oh, I thought you had something in the comments. Is if you're on a mechanism like this that has hard stops, you're going to have to go max speed on the joysticks, but let go before you actually crash. That's why I recommend doing this the first time on a drivetrain, because you can continue to run that drivetrain forever without crashing as long as you have the robot blocked up. So I'm going to hold down the joystick and go full speed till I get about half or 3/4 of the way up. And I'm going to disable the robot so we can see what information we had here. You can see when I was holding the joystick here, we're getting a +1, and we reached a velocity of 43 units per 100 milliseconds is how this comes out here. And we're going to record this value of 43. So now we know that our robot can go from 20 to 700 and it's at a speed of about 43 sensor units per 100 milliseconds. Now is when we're going to want to go look at our this worksheet that it was linked to inside the chat where it's what was that URL called there? Can you give me that URL? Tiny URL, Grand City or GCGH, Motion Magic WS, MSWS. Now I'll bring us up to this worksheet here that I'm going to pull up. This year worksheet has been based off of the JVN. There's some JVN data worksheet, but we're using it for Motion Magic. So what you want to do here at the top is select the motor. Today we're using the 755 Pros and an analog feedback device. We're going to enter in here the units per second of what we measured, and we've seen 43 with that fresh battery. You can see the green areas are the areas that we're going to input information. The yellow areas are feedback back to us. With this measured feedback, we're seeing about 25 RPM is what's happening at the encoder. If we do a little sanity check here, knowing that the 755 Pro is 18,730 RPM, the gearbox that we're using today has 2 of those 755 Pros on a 30-8 gear reduction, 2 motors into 1, going into that planetary gearbox, which is a 21 to 1 today, and our 10-turn potentiometer. We have an effective gear reduction to the encoder of 787.5. If I enter that number in here, we can see that the calculated speed of this is supposed to be roughly 24. So we know we're in the neighborhood, we're collecting good data, and that's just a sanity check to make sure that everything is happening as we would expect. This is also giving us our F gain parameter right now of 23.8 for today. So this is what we're going to go enter into our code. So we're going to record 23.8 as an F gain. And we can also now start to make some choices of how fast we want our mechanism to run. We're going to say we want this elevator to only operate at 75% of max speed to give us a little overhead. And it's good to start out low and then bring this up slowly as you feel more confident things are working. And we also say we're going to want to take 1 second to go from 0 speed to the max cruising speed and back down from the max cruising speed back down to 0. So with those values of 23.8, 32, and 32, we can start filling in some of these blanks here. Our feed forward was, again, 23.8. Our velocity, 32. And this has to be an integer, not a decimal. And 32. We'll hit save. We'll deploy. Clear our console here. And now I'm going to jog this robot down to the bottom here using just the joystick. But now we can remember we set those points from 20 to the bottom, 700 to the top. If when I click the Y button, this will now run our motion magic, slowly accelerate and decelerate into position, as well as the A button back down. The down, we have gravity helping us here. So that's why it crashes a little bit more, and we can look at that here in a bit. But we hit our position right here, and I'm going to disable the robot and take a look at some of the output that's being displayed to us. So you can see as we drive up here, our position is, or our output is paying attention to that 75%. There's our velocity, and our error is roughly 35. And as we approach our position, our target position 700 and our actual position is 670. We have a steady state error of around 30. We can go back to our worksheet and enter in this given error of 30. Yeah, 30. And you can see that this formula right here is it's giving us a P gain of about 3.4. We're going to come back to our motion magic and we're going to go fill in our P. We'll save here. We're not going to look at the I and D right now. We'll re-download this. And as this is downloading, this particular elevator here is geared for more power because they're a climber. And if I didn't mention it before here, we borrowed this robot from 3023 Stark out of Elk River. Last year's game didn't have a whole lot of arms and elevators compared to the previous 2 years of our pick and place games. That's finished downloaded. We'll re-enable this. I'm going to try the motion magic again. I'm going to use the A button. It's a little bit softer because we have that P control helping us. When I disable the robot here, look at the steady state error. We're now closer to when we were at 0. We overshot it just a touch. So it's a great example on the overshoot. If we want to start really dialing this in there, if we want accurate position, that's when we're going to start using the D and the I terms. What the D term does is helps us get to position. If sorry, check that. The D term holds back on the horses a little bit so we don't overshoot. And the I term is that if we need a little extra boost as we get there, we can turn on the I. And the I is an accumulative value, and that's why we want to make sure we have our zone. So it only is being applied when we hit our set point. So we can go back to our worksheet here and take a look at some of the suggestions. So just using these formulas here, and there's links on this worksheet to the Phoenix documentation of how these formulas all work. We're going to use a D gain. We're going to enter in our final, actually we're going to enter in what we find. We'd go back and forth if we weren't getting a position here. Enter in what we finally put in. So today we used a 3.141. And they're saying a D gain of about 34.1 and a really small I gain of 0.001. What was the I? 0. We're going to resave that. And deploy. Re-enable our robot here, 0 our console, and try some more movements here. Lot smoother control, and as I'm holding that position, you can see our steady state error is hovering that around that 1 and 2. That I gain is trying to really zero us in there. So really in only a few minutes using some sample code, we've now got a smart mechanism on our robot that we can program to go in a number of positions anywhere within the range of its motion. The next thing we might want to start looking at, and especially in the years past when our elevators were more about speed and less about power, where if we're holding these heavy mechanisms and just as it sat there by itself, it would want to fall. So we want to start applying a term called arbitrary feed forward. But is there any questions up to this point? Nothing yet? Okay. Well, with that, we'll keep on. Let's make sure I'm not skipping over anything. So the arbitrary feed forward. With an elevator, it's really simple. I'm going to comment out some code here. In our loop, how we're going to calculate is we want to figure out something called horizontal hold output. How much power does it take for the motor itself to hold the elevator in position? As you can see right now, when I'm touching no buttons on this robot in the console, the output's at 0. But if with holding no power in here, if this elevator had a heavy mechanism on it, it would start to fall down. We want to know what's it take to actually hold this elevator. So let's try to imagine a little bit that I have to hold this joystick maybe at 0.13 just to hold it in position. Now you're going to want to look at the video I kind of hinted to from 973 back in 2016 of building your mechanisms so you don't burn up motors. A lot of these 755s and the like motors, if you stall them, they'll catch fire. Now there's a point, VexPro has some charts on their website that can show you that you can stall these motors using 2 volts and it'll last the life of the game without burning up. So that's where we try to target that 0.13 or so. I'm going to disable this robot. Just jumped on me. And then what we're going to do is we're going to start adding this term, this feed forward to the motion magic. So we can see right here, we're using the control mode motion magic just as a 2 parameter set. But if we add these other 2 parameters for the arbitrary feed forward, too much.
We got a question for you here, Corey.
Yes.
Let's see here. We got, wasn't the recommended D gain from the spreadsheet 34.1, but the value put in the code for D was 3.1?
Very possible. I'm typing this out of memory here. Let's go take a look at that worksheet. Yes, it was. So and tuning the PID controller is a back and forth where it takes a few times, and I am skipping over it pretty quickly, and I'm doing it a little bit faster than you'd want to in actuality. Time is it? We got about 15 minutes left, so that's good. That's going to affect things here a little bit. And what that D term is going to do is really for that bottoming out. It's going to prevent us from overshooting. It's going to hold back the horse a little bit and soften that bottoming out there. So back to the horizontal hold power, this 1.3, and to be able to see what this is going to do, and we're going to talk about this in a minute, and if I don't at the end, please remind me to, somebody in the room, is I do not want to put this robot into percent output mode. I'm going to make sure that it stays in Motion Magic. I'm going to save this. And using this holding term, and you remember before that this robot, when we pushed up on the joystick at 0.13 command, it did slightly drift. So and elevators are easy because we're just dealing with gravity. When you start talking about arms, and we're going to go look at some sample code of that here in a minute, you actually have to calculate the current position, the current angle of the arm, and calculate your hold feed forward term relative to the angle. A to go bring it down. You can see that D term really softened that up again. And that's that arbitrary feed forward that value, and they're making it drift and go all over the place. That'd be very important if we had that heavy load elevator. So I'm gonna put that currently at 0 because this mechanism here is not a very good example of that. So finally, if we were looking at an arm, we would want to go out and calculate our arbitrary feed forward. So we wrote a method here at the bottom here. It says get the feed forward term. And instead of putting the horizontal hold power there, we'd want to, again, this is for more of an arm, get the arbitrary feed forward term. And if we go look at this method, we're passing in the hold power. So what it takes to hold that robot at 0 degrees. And what it's going to do is we have to convert that number or get the current angle of the robot, which on this code here, to get a 0 degrees here, standing straight out there, we went out and got the angle of the potentiometer, return the angle, convert it to radians. Then we take the cosine of that value to get the gravity compensation. And then we can take the gravity compensation times what it takes to hold it at 0 and give it an arbitrary. So when we're at 45, we're using 50% of the gravity compensation. And when we're at 90 degrees, we're using 0%. And that will prevent it from smashing at the end of strokes. I can't demo that there today on this particular robot, but quickly, that's how that is, how that might work on an arm. Now, just a minute ago, you've seen how I commented out, this is at 0, so that's good. I'll put this back here. I want to kind of do a safety tip here. At 0. So if we push 1, it's going to go to the max. If we push button 4, it's going to go to the lower target. And we do not have this control mode percent output. What's going to happen here is, yes, the robot's going to work just fine on the field and outside the field. But if we command the robot to go max up, we disable the robot, and for some reason, somebody in the pits goes and moves the elevator or moves the arm on you. As soon as the robot's re-enabled, it will go right back to that position, but it's not going to pay attention to the command velocity or the ramp rate. It's going to go saturation until it gets there. I'll show you briefly what that looks like. Enable the robot. I'm gonna go to the max height. I'm gonna disable the robot. Somebody moved it, and you can imagine if this was an arm that was commanded to go down, somebody moved it up, and the robot was re-enabled, the arm's gonna come smashing down and potentially injure somebody. Enabling the robot made that move again. So what's a good idea to do? We'll disable that robot. In every one of your teleop period or teleop init methods or autonomous init, or even the robot disabled init, which doesn't exist in there here. You're going to want to call your Talon and set it to control 0. I hope I got, did I get that method right? Can somebody tell me? My joystick don't do anything. So A. Disable the robot. A little bit. I bet you I called the wrong method, didn't I? That was off the cuff there. I gotta go get a reminder here. Unless somebody gets me in chat before I can go find that. Oh, good. It's a race. There it is. Forgot to put the override in there. Those links also link to all these slides as that's downloading here. All the different steps and things we talked about. This is kind of what we're talking about right now is the Talon SRX control mode will remain in the last state, robot disabled. So you want to make sure you call that control mode % output and set it to 0. Disable. It'll be easier to pull it down. Re-enabled and the robot didn't take off moving. So it's a good idea to make sure you're putting that code away to put the Talons back into a % output mode. Anything else that you'd like me to get a little closer on there? That is in a nutshell. the demo. Any questions in the room? 19 crickets, is that what we got? Maybe in the chat. What type of robot programming do you use? Now, I demoed this in the Java, but it also works in C++. But do you use the robot timed robot or the command-based robot? So, right, the command-based robot. What you seeing? Oh, so I do have a sample here. So this is in the timed robot. And what you're going to want to do if you're using the command bases, have this program working on all your subsystems that you do motion magic.
Yeah, let's see. We got it says, can we simulate this using any tool without actual motors to see if our profile works correctly?
I am not aware of that particular question. Maybe somebody, I'm going to come up with an answer on that. And we'll see if we can't get something documented in those for you. I've always had a live robot to do the work. And I know the new tools have a lot of, the new WPI libraries are going to have a lot of simulation stuff, but they're not going to be for third-party libraries. So this is definitely with the cross-road electronics stuff. If you're using the command-based model, I do have, I believe it's this guy right here. Yep. You're going to have your normal subsystems and your robot and your commands. And what you're going to do inside your subsystem is really copy all of these variables at the top of your subsystem, and everything in the robot and init, you're going to put in the subsystem constructor. You're not going to have a teleop init or a teleop periodic, but in the periodic, this is really the area, especially here, you're going to create a method to call this motion magic target position and send it a variable like you would with from a command. If you go look at the motion magic sample here, we see the motion magic subsystem at the top here. We copied all those setting up the variables in the constructor, all the configuration of those variables. As well at the bottom, we created two methods, my motion magic, a target position, no arbitrary feed for it in this one, and also a way to set it to % output speed. And then in the command that would talk to this, we see that when we call this command, we set it a set point, set this internal variable, and this one has not been completed, but really in the initialize, we could call robot dot motion magic dot what was that called up there? M set point. So when we initialize the command, a few minutes here, and also in the end is where we would call that way to, if we didn't want the PID controller to hold it, we'd use the end method here to put it back into % output. Also, as I kind of stated before, and I can't stress this enough because somebody's going to get hurt if you don't do this. You go into the robot file in your command base, and probably the best place to do it is always in the disabled init, always, no matter what, because as you cross between the different modes, you'll be always going through this method here. But just to be super safe and not sorry, put it in all three inits. And that way, you know, and you're going to want to call that out every subsystem that uses motion magic.
just a question on the spreadsheet, because that's I think a huge part of this, right? If I had always seen things about how you tune and you need the mechanism there, and you just go increase P till it oscillate, you get oscillation and then back it off by one step and whatever.
Yep.
That's huge to have the actual calculated values. In the orange box, what are you looking at there? How is that orange box used relative
This one
to
is
the rest
really
of the
specific to our robot.
Mhm.
There's several different stages. So the first stage of the motor is a 30 to 8, where the two 755s are going into the one planetary. The planetary has ring gears set up for 21 to 1. And since we're using a 10-turn pot, really what this calculation is the gearbox between the motor and the feedback sensor. Now,
Yep.
if there was more gearing, if you had that feedback device right on the back of the motor, then that would be essentially a 1-to-1.
Gotcha. And that's all kind of a side calculation to get the green box over on A9, right? Says the
Yes, exactly.
Okay. All right.
So that's really, this value right here is the value you need between the motor and the feedback device for the ratio.
Gotcha.
It has nothing to do with the mechanism that you have. In this particular case, it is at the end on the very output of all gear reductions. But if you're using the CTRE, just magnetic encoder, say maybe like on the second stage of a gearbox, you want to know what that first stage gear reduction is, but ignore the second, third, and fourth, or any other gears or chains on the output of that.
In your experience, is there benefit one way or the other to where you put the encoder relative to the, is it, we always thought, if I want it on the output shaft of, the mechanism, wherever the motion is going, so that then the units are kind of something you can visually see relative to the mechanism, as opposed to like at the motor, it's which may spin a whole bunch of times or something. Do you have any recommendations? Is it better one way or another? Or?
In first, I don't think it matters too terribly much. Now, with the drivetrain, that is an absolutely true statement, just because we're trying to position a robot, drive some distances, and there's all the backlash. So if you put it on the output shaft, you get rid of all that backlash because you're measuring the actual device. Now, we have used this, and I just switched it to quadrilateral encoder right on the back of a 755 or a redline motor, and we had equal success with that as well. But we weren't trying to do exact placement. And even with elevators and arms and first, that little bit of backlash just in there, usually the game allows us quite a bit of fudge. You can look back to Deep Space. When we placed that hatch, I remember in the beginning, like, wow, that's exact, right? We have to hit this Velcro just perfect to get it stick. And it really, in the end, you could almost frisbee the thing up there. You just had to have it block the ball or the cargo. So really design the feedback where it makes sense for the mechanism, and just make sure you design it and get it in there. From there, you can scale. Even if it's on the motor itself, you can take those units and scale them to something real. Now, in this sample code you see, I was just using encoder units, but it wouldn't take much to measure that 20 to 700 and convert that to an actual,
like feet or inches or
feet,
something.
inches, or whatever user unit we call them in industry, and then enter in a user unit to a position, and then have your method reconstruct the native units from that. Super handy if you're doing a pick and place, because they come in the pit and say, I wish we could go up 2 inches higher. Well, honestly, I know our elevator, our deep space elevator, it used encoder units, and our programmer just knew that 10 is about this far.
Is with Motion Magic versus Profile, in Profile lets you put in a path and things, right? Are there ways, I haven't dug into it enough, but where you just say, instead of go to a position, you can set velocity, and then all the things that you've done so far work seamlessly for that too? Like you set a velocity set point instead of a position.
So you
For
wouldn't
a
use this in
drivetrain?
Motion Magic. You'd use that in there. I don't know if I can have time to get there. Kind of at the end here, which there's nothing but up against us. I know I have it in my downloads folder. They have a velocity. If you're trying to do more like a flywheel, you'd probably download this velocity closed loop program and set that. And from there, the feed forward testing that I did would work perfectly for that as well. And actually, I helped CIS last fall with their flywheeler, and that's what we did. But you can see right here in the Java, there's all these different configurations and sample codes of way you could use their controller.
Is the tuning all the same, meaning the spreadsheet and all the ratios and P's, and or what you're saying you had to do that extra feed forward step after you do those initial tunings to use velocity efficiently?
Very similar.
Okay.
We go back to my spreadsheet here. You see when you download this, you can see the Motion Magic closed loop walkthrough. I can click on that link and it'll bring me right to the page here. And they have really good breakdowns on how to do the velocity versus Motion Magic.
Okay.
And basically everything I just demoed is starting at the top of this motion controller closed loop, calculating feed forward. This ain't special to Motion Magic. And then you start going into the Motion Magic part.
Great, thanks.
Yes. Any other comments or discussions? Otherwise, what time does this end?
We're a little over, but that's okay.
Oh.
There was some good discussion, so it was great.
Oh, so you didn't break me in. Okay.
No.
Last time I was the first session, so I got cut off.
No, you're good.
Well, thank you, everybody. And I hope you guys are all signed up for December 5th Jumpstart. Those classes are being populated right now, and they should be published soon. So till then, we'll see you.
Thanks, Corey.